begin the session. So what is a tree? Tree is a non-linear data structure. Yes. We arrange the elements in the tree in hierarchical manner. Yes. It consists nodes. Yes. Connected by edges. Yes. We all know that. If you want to go for tree, we have some basic terminologies in the tree. First of all, we always have a rooted tree, means our tree starts from a specific node which we call as root of the tree. Then we have child. What is the meaning of child? Look at this. 7 and 5 are children of 2. Then 2 is child of 7. 10 is child of 7. 6 is child of 7. Right? 9 is child of 5. 4 is child of 9. Like this. If 7 is child of 2, then what is 2 for 7? 2 is parent of 7. Similarly, here 2 is parent of 5. Parent. Right? Sibling means those nodes which are having common parent, like 7 and 5 are sibling of each other. Why? Just because having common parent. 6 and 9, no. Why? Just because 6 and 9 are on the same level but not having common parent. 7 and 5 different parents 6 and 9 are having, so these are not siblings. Siblings means those nodes which are having common parent. Then subtree means a tree starting from some intermediate node. This is subtree starting from 7 as root. This is subtree starting from 5 as root. Like that you can define subtree. Then we have internal nodes. Internal nodes means nodes with children. The nodes which have child. If at least one child is also present, that is internal node. Like this. These all are having children. Remaining nodes, if not having children, then what these are called as? External or leaf node. The external nodes or leaf nodes do not have any child, no child. So if node can have either child, cannot have any child. Right? Understood? Then handshaking lemma. Handshaking lemma is nothing but when you have total number of nodes will be equal to number of leaf nodes plus number of internal nodes. Why so? Just because every particular node can be either leaf node or internal node. That's why. Good, Sabha. Parenthesis representation of a general tree. Right now we are discussing a general tree in which there is no any restriction of the children. There is no any restriction of the keys or anything else. Right? As many as children a node can have, no any left right key restriction, no any arrangement restriction, nothing. So how to represent such kind of tree? Using parenthesis. How you represent? First of all, you write root, in the bracket all the children, or in the parenthesis all the children separated by comma. Child number 1, child number 2, and so on. Might possible these of the children can be a root of a subtree. So you can take this as a root, and then you can in the nested way represent the entire tree. Fine. Let's go ahead. So root is 2. Root is having 2 children, 7 and 5. So 7, 5. Now what happens? Can you guys confirm my voice audio video is clear? Can you guys confirm my audio video is clear? Okay, so yeah, so after 7 is having more children. Yes, so after 7 I'll have to have its children in the bracket. After that I'll put the comma. Entire subtree will be written. After that I'll put the comma. So 7 is having 3 children. Yes, 2, 10 and 6. 6 is having 2 children, 1 and 11. 1 and 11. 5 is having 1 child, 9, and 9 having 1 child, 4. Okay, all clear. Good. All these store in array? Yes. This parenthesis representation will be stored in an array so that we can access the entire tree. Like, okay, root is 2, its children are that, and those. Of course, it's not a very, you know, efficient method. Why? Just because to access the child of 2, 7 and 5, it's very tedious task to find where is the children. That's why linked representation is better, which we see in the binary tree, right? Okay, so what is the height of the tree? There are two definitions of height. One definition is the root will be considered as, or single node considered as 0 height, single node considered as 1 height. And based on that, we will be having two different definitions. But before that, we need to know one particular term here, which is level. If you don't know about what is a level, level starts from 0. Yes, root is called as at level number 0. This is level number 1. All these nodes are at level number 2 and level number 3. These are different levels present in the tree. Okay. Now, what is the height? We can say height of a tree is maximum level number, which is 0, 1, 2, 3, or maximum level number plus 1. The same way, two different definitions are there. The same way can be written. If suppose single node you have, how many levels you have? 0. So, single node height 0. Right side single node height 0 plus 1, 1. Maximum level number plus 1. If you have no any tree, empty tree height should be 1 less than single node, which is यहाँ अगर 0 है -1. If single node height 1 है then 0. The same thing can be written in terms of length. How? What is the length of path from root to the farthest leaf node in terms of number of edges? 1, 2, 3. Height of the tree is 3. The same thing in the right side, other definition says that number of nodes you are counting. Number of nodes 1, 2, 3 and 4. You can count up to here also, you can count up to here also. All are farthest leaf nodes. Right? So there are two definitions of height. The height, one definition says 3 for this tree, another definition says 4 for this tree. Got it? Okay, now next thing is, if you understood height, you will have to understand always that there is no any default definition. Any definition can be used anytime based on given in the question. So you will always get a particular definition given, use that particular definition. Whichever definition is given, you'll have to use it. Always given in the question, yes. Height of the tree recursive approach. How to do that recursive approach? First of all, if you want to calculate recursive approach, first of all, you need to have the base condition. So what is the base condition? Base condition is, if tree is empty, what should be the height? Either 0 or 1, depending that which definition you are implementing, this one or this one. So the base condition is what? Base condition is empty tree height is what? Empty tree height you need to get either 0 or 1. After that, if tree is not empty, how do you calculate recursively? First calculate height of left subtree completely and calculate height of the right subtree completely. So you will calculate height of the left subtree recursively, then height of the right subtree recursively. After that you will compare which one is maximum. Which one is maximum? If height is more here, my entire tree's height will be dependent on the left subtree side. If height is more here, my entire tree's height will be dependent on right subtree's height. Whichever is more, my entire tree's height will be dependent on that. So what I'll do, I will get the left subtree's and right subtree's height and I will compare which one is maximum. If this is 2 plus 1 is height of my entire tree. Why plus 1? Root को include करना पड़ेगा. We will have to include the root. If this is 3, maximum is 3. 3 plus 1 is my height of the tree. So what exactly I'll have to do? I'll have to calculate this HL and HR, left subtrees and right subtrees height, and I'll have to return the height. I'll have to return the height of entire tree is equal to maximum of these two. HL, HR plus 1. लेफ्ट सब ट्री और राइट सब ट्री में जो मैक्सिमम है, विच एवर इज मैक्सिमम प्लस 1 will be the height of entire total tree. Yes, Nishu, good, superb. So here I have written, I have called height function with binary tree type pointer t, which is pointing to the root. I am checking if root is null, not of t, true. When root is null, then return 0. So this says empty tree height 0. Empty tree height 0. Empty tree height minus 1 means we will have the other definition. Empty tree can have height either 0 or minus 1. Right now empty tree height 0 means single node height 1 we are considering. After that remaining thing is same to same. Recursively call the left subtree's height and get the height returned into Excel. Then recursively call height function for right subtree. Get the value in HR or XR. Then after that compare which one is greater. If XL is greater, return XL plus 1. If not, then return XR plus 1. So this is the recursive approach for height. हाँ जी बिल्कुल 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 यहाँ पे 0 और -1 होगा, बिल्कुल ये -1 होना चाहिए बेस कंडीशन, ये लो. यस, एम्प्टी ट्री हाइट इधर 0 और -1. करेक्ट, आई मेड इट करेक्टली. ठीक है, चलो आगे बढ़े. लेट्स गो अहेड. सो आई हैव रिटन दीज टू डेफिनेशन. This particular definition is for what? This particular definition is single node height 1 and empty tree height 0. Similarly, when I will return -1, what does it mean? Single node height of the tree is equal to 0, and when the tree is empty, height of the tree will be equal to -1. So both I have given. Okay, fine. Let's go ahead. That's a binary tree. A tree in which each node has maximum of 2 children. Maximum of 2 children means minimum can be 0. A tree in which each node will have either 0 child or 1 child or 2 children. 2 से ज़्यादा नहीं, more than 2 not allowed. That is the binary tree. Okay, so what is the benefit of having binary tree? We can divide the tree into 2 parts always only. So in that particular case, restriction is there. Yes, restriction is there means it will be a better way to represent any data structure. More restriction means the algorithms will be better. Fine. Okay, now so binary tree, how to represent binary tree? This is the binary tree, but representation of binary tree becomes easier than this. What is the meaning of actually representation? Representation means if I'll have to run any code, any program, any kind of algorithm on the binary tree or any tree, how will I store the tree? ये ट्री तो दिखता है, आई कैन सी दिस इन ग्राफिकल मैनर, बट माई सी लैंग्वेज डजंट अंडरस्टैंड ग्राफिकल मैनर ट्री, राइट? सो आई हैव टू स्टोर दैट ट्री इन सम फॉर्म so that my algorithm can run on it. Yes, parenthesis representation is not so convenient. To find the children, it's not directly accessible that which one is child of what. So because of that, this is very good approach, which is the linked representation. What linked representation says that? Linked representation says that every node, this every node will be represented by a linked node. In this particular node, you will be having 3 fields. One is left child, right child pointer, and key. Key means the value label of the node where you are keeping, what you are keeping on the node. And then 2 pointers. One pointer is making you to reach to the left child node, and right child pointer holds the address of the right child node. So how exactly you will write the structure of this? You will write a structure for this. Yes, struct binary tree type node. This is the structure. This structure will have 3 types of fields. First member is a character type of key. The name of this particular key, you can have data, value, whatever. Then you have left child pointer. Yes, what type? Struct BT node type pointer. Struct BT node type pointer. Left child, I am just writing LC in short. And then another pointer, same binary tree node type pointer. Right child. Right, now look at this. Oh, this, if I want to represent this particular tree in that linked representation, how will you define this? Very simple. First of all, there will be a tree pointer or root pointer pointing to my first node. First node is holding the value A. बड़ा हो गया ज़्यादा. Holding the value A. This node is having three fields: key value A, left child pointer, and right child pointer. What is left child pointer? Is holding a node, another node which is holding the key value B, and left child pointer, right child pointer. Left child pointer is holding value C. C is not having any left and right child, so here we will keep null pointers. Here also I should keep null pointer just because there is no any right child of B. A is the right child D, so node should contain key value D, left child E, right child F. These will be the pointers which I have shown here as arrows. E and F are not having left and right child, that's why we will keep null pointer. Okay, chaliye. Now the thing is, if suppose in this particular tree I have given you a pointer, let's say T, which pointing to some node, any node, and I am asking that T pointer pointing to a node, that particular node is a leaf node or not. How to detect that? कैसे डिटेक्ट करोगे कि T पॉइंटर जिस पॉइंटर या जिस नोड को पॉइंट करता है वो लीफ नोड है या नहीं? I'll have to check what is the leaf node's quality or property. Leaf node's property is, leaf node is that particular node which is having both left child and right child not present. No any child present, no means what will be the pointers in pointers term, what will be stored in the left child pointer and right child pointer? Null and null, like this. C is leaf node. Why? Just because left and right child both are null null. Here also null null, here also null null. Right? B is a leaf node? No, its right child is null but left child is not, so it is not a leaf node. So how to detect a leaf node? If pointer P points to a node, pointer T points to a node, I'll have to check if pointer T ka left child is equal to null and T ka right child is also equal to null. If that is the case, then of course I can say T points to null. Points to a, sorry, leaf node, not null, leaf node. T points to a leaf node. Good, Pratibha. Nice, nice, nice. Now in the binary tree handshaking lemma, if you remember the handshaking lemma of binary tree, it's very simple thing. Number of leaf nodes is equal to, we represent number of leaf nodes as capital A in our program. Whatever the discussion we had, number of leaf nodes, capital L, is equal to number of nodes with 2 children plus 1. Number of nodes with 2 children, which we represented as I2 plus 1. And how many total internal nodes we can have in the computer system? Total internal nodes. Two types of internal nodes are present in the binary tree. Internal node with single child, internal node with 2 children. So total internal nodes will be equal to internal node with 1 child plus internal nodes with 2 children. Good, Sabha. Right? Now, total internal nodes are these. Total external nodes are these. Total number of nodes just now we have calculated, right? Total number of nodes is equal to total number of leaf nodes plus total number of internal nodes. So total number of internal nodes I1 plus I2, L is equal to I2 plus 1. I will put the values here. Total number of nodes capital N can be denoted by twice of internal node with 2 children plus internal nodes with 1 child plus 1. Will that be fine? Now you will remember I1 is internal node with single child, I2 is internal node with 2 children. Total internal nodes can be internal node with single child plus internal node with 2 children. कुछ internal nodes ऐसी होंगी जिनका एक child है, कुछ के 2 child है, तो total कितनी हो गई? दोनों को मिला दो, ऐड कर दो, इतनी internal nodes. Now total external nodes कितनी होती हैं? इतनी. Then total nodes will be how many? Total nodes will be internal nodes plus external nodes. Internal node I1 plus I2, external nodes I2 plus 1. We have added, we have gone for the entire. Yes. Chalo. Next question is, how many binary trees can be constructed using n unlabeled nodes? Unlabeled means there is no any labeling. There is no any labeling. Empty nodes are there. So answer will be, if you remember, there is a formula called as Catalan number. There is a formula, yes, Catalan number. So number of binary trees constructed using n unlabeled nodes is Catalan number, which is 2n Cn divided by n plus 1. No key is there. Key nahi hai. There is no any key. Okay. Now if key is there, then if you have n distinct keys, then what will be the number of binary trees we can construct? It's a binary tree, not binary search. Binary tree, answer will be whatever the unlabeled nodes we are having in each tree. Each tree we are having n factorial possibility. So this one into n factorial. This one into n factorial. Right? So number of binary trees using n distinct keys will be these many tree you can construct using n unlabeled nodes. Now within each tree you can populate the keys using n factorial possibilities. So into n factorial, multiply by n factorial. Got it? Next is this binary tree representation of a general tree. एक general tree को binary tree में represent करना पड़ेगा. क्यों करना पड़ेगा? Why we need that? Just because the general tree we cannot store as a linked representation. Why? Just because general tree is not having limited number of children. It can have 1 child, 2 child, 3 child, 4 child, 5, 6, 7, 15, 20. A node can have 100 children also. So how to represent that in linked representation? It is difficult. Why? Just because in binary too we know every node can have maximum 2 children. Yes, so we will have each node created with only 2 pointers. Fine. But if we will have 2, 3, 5, 10 unlimited number of children, how many pointers you will create? You don't know. So binary tree representation type or such kind of linked representation we cannot have of general tree. But we want that linked representation should be there. Yes. So there is a method through which you can convert a general tree into a representation kind of a binary tree. Kind of a binary tree. Okay, fine. All those members who are getting difficulty, why this and why this, so please go through my data structure full length playlist in which I have explained how this comes, how this into n factorial comes. I have already explained every single thing in much more needed detail. Okay, so binary tree representation of a general tree is nothing but tree is general tree only. We are trying to store it in the terms of in the way of binary tree, and that particular method is called as leftmost child right sibling representation. So what exactly we are doing? We have in background general tree, but we want to store that general tree into linked representation, kind of a binary. Though in background you have general tree, yes, general tree is general tree, we are just representing it in some different way so that we can store it in the linked type of representation. How? I will tell you now. So let's take as an example that we have a general tree like this: A, B, C, D, E and F, G, H and I. What it says? The method is very simple. Starts from root. Start from root. Represent this into binary kind of representation which we can store in the memory so that we can run the algorithm on the linked representation. Right? But the tree is this only? Yes, tree is this only. Original tree is this only. Now look at this. What it works? Leftmost, in the left we will have child. In the, for every node in the left we will have child, right side mein we will have sibling. In the left side we will have child of node, right side we will have siblings of node. So what is the child of node? Child of node, A ka child, but we will check out from the leftmost corner, leftmost child. What is the leftmost child of A? B. So it should come in directly A's children B. That's it. Yes. In the right side, we will have sibling of A. There is no any sibling of A. Fine. For B, leftmost ka pehla child, the first child from left side E. In the left. Right side sibling of B, C. E's leftmost child. Leftmost child, is there any child? No. No leftmost child. Right side sibling of E. Sibling of E is F. For C, leftmost child in the left. No any child, no. But right side sibling. So sibling of C in the right side. D. D. Leftmost child. Which is the first child from left side? G. Left side. Sibling of D in the right side. No any sibling. G. Left se pehla child. The very first child from the left is H. First child of G is H. Should be in the left. Right side G ka sibling. There is no any sibling. H ka leftmost child in the left side, yes. Right side sibling, no. This is the tree. So ये general tree है. We can have more than 2 children, 3 children, 4 children, 5 children of a node, yes. But we will have to represent that in a binary tree kind of representation. Why? Just because we can store it in a linked type representation. One side left, one side right. In the regular binary tree, normal, if it is a binary tree only, left side mein left child, right side mein right child. But here left side is child, which is the first child from leftmost side, and right side mein we will store the sibling. That's a representation. It's a representation. Okay, Rahul, here we cannot explain particular things just because it's a revision class. It's not an explanation class. You just once check out my explanation class. I have explained this one in really detailed manner. Fine, chalo. Next thing, multiple free pages got added. Delete karo isko. Minimum and maximum number of nodes in a binary tree on a level number L. Before that, okay, let me go back and let me ask you a question. Why we are doing this? As I told you, to store general tree, we cannot have linked representation. You know? Yes. So how we were storing that general tree in a parenthesis representation? But as we told कि सर parenthesis representation में algorithm चलाना आसान नहीं होता, तो आप linked representation में ही लेके दो हमको. तो what we did, we have transformed our general tree into linked tree type of representation. So linked representation type of representation, I made it. Fine. In that, in the left side of every node we can have only child. हर एक नोड के लेफ्ट में आएंगे उसके चाइल्ड, राइट में सिबलिंग ही आएगा. सो लुक एट दिस, हियर वी हैड जी का ओनली चाइल्ड एच. I have drawn it in the right side, but there is no any distinction, there is no any differentiation of left and right in general tree. General tree में left right का कोई distinction नहीं होता है. लेफ्ट से पहला चाइल्ड जो भी आएगा वो लेफ्ट में ही आएगा. तो G के लेफ्ट में हमारे पास H आएगा. क्यों? क्योंकि H इज द चाइल्ड ऑफ G एंड इट शुड बी इन द लेफ्ट ओनली. राइट साइड में सिर्फ सिबलिंग आएंगे, सिबलिंग आएंगे. Right side we have only sibling, left side we will have child. Now if somebody asks you that this is the right leftmost child, right sibling representation of a tree, can you tell me what are the nodes which are leaf nodes? Leaf nodes, E is leaf node, F is leaf node, C is leaf node, then I is leaf node. These are the leaf nodes, E, F, C and I. Why? Just because those are not having left child. Those are not having left child. Those are not having left child. लेफ्ट मोस्ट में रहेगा चाइल्ड, राइट में रहेगा सिबलिंग. लेफ्ट से पहला चाइल्ड लेफ्ट में, राइट साइड में आएगा सिबलिंग ऑफ द नोड. वी कैन नॉट कीप चाइल्ड ऑफ अ नोड इन द राइट साइड. Right? So if we are keeping in the right side something, that is the sibling, not the child of any node. A के जितने children हैं all are in the left side. B के all the children are in the its left side, E and F. D's all children are in the left side. Right side only sibling. Understood? Leftmost means the very first from the left side should be in the left. Right sibling means right side से sibling. Right में only sibling, left में child. Got it? Sure. Minimum and maximum number of nodes in a binary tree on a level number L. On any level which is having a number L, minimum number of nodes can be 1. How? If you have a tree like this, any level can have single node. So minimum is 1. Maximum. How many maximum number of nodes are there on a level number L? Let's say this is the maximum tree. This is level number 0. On this, how many nodes are possible? If level number is 1, how many nodes are possible? If level number is 2, how many nodes are possible? If level number is 0, maximum number of nodes possible is 1. If level number is 1, number of maximum nodes possible is 2. Level number 2, maximum nodes are 4. Level number 3, maximum nodes are 8. Level number L, maximum nodes are how many? 2 power L. Simple. Good. Nice, Sabha, Pratibha, Nishu. Good. Superb. So maximum at any level number is equal to 2 power L. Next, minimum and maximum number of nodes in a binary tree of height h when height of a tree with single node is 0. H is equal to 3. 0, 1, 2, 3. Number of nodes are 4. Minimum. Each level single node height will be 3. Number of nodes are just 4. Minimum will be equal to h plus 1. What is the maximum? You remember the formula? If not, then create the tree as soon as possible. You see that. Construct the tree. Height is equal to 2. Number of nodes are 7. If height you increase at 3, number of nodes will be 15, which is 2 power h plus 1. Okay, let me write capital H. 2 power h plus 1 minus 1. Good, good, good. क्या बात है, काफी सारे लोगों को आंसर पता है. Wow, nice. Good, great. Okay, let's go ahead. Next one, tree traversals. Important topic. Yes, very, very important. So in the tree traversals, we have 3 types of traversals: pre-order, in-order, post-order. What pre-order says? Pre-order says we will have to traverse first node, then left subtree in the recursive manner, then right subtree. Inorder traversal says node should be traversed in between. First of all left subtree, then node, then right subtree. Post order says node will be traversed at the end, means first of all node, then left subtree, then right subtree. Oh, right, ulta लिख दिया मैंने. At the end node will be traversed. So first of all left subtree, then right subtree, then node. Let's get the traversal of this particular tree. First of all pre-order traversal, root, then left subtree, right subtree. In-order traversal, left, root and right. And here in post-order traversal, first of all left and right and root. If you want to write the algorithm, you are calling the pre-order function using the binary tree root pointer t. You just check if t is true, then only you do some kind of traversal. In the traversal, what you will do in the first place, you will print the data of the current node, traverse the current node. After that recursively call left child के लिए, recursively right child के लिए. If we will go for in order, in order only changes, we will print the value after traversing entire left subtree, then print, then right subtree. And then for post order, printing will be at the end. First of all post order recursively for left child, then right child, and then print the data at the end. Why? Just because in the post order we are traversing the current node at the last after its left and right subtree. Okay, fine. चलिए अब dot method. If you remember the dot method, well and good. Otherwise I'll remind it you again. If pre-order में you traverse the node before its left and right subtree. Traverse the node before its left and right subtree, right? So put the node pointer or a dot before left and right subtree here in the left side. Why? Just because we start from the left first here. Put the dot and after that start from the root. Take a boundary, such kind of traversal for all the nodes. Sequence of dots will give you the pre-order A, B, C, D, E, F. A, then B, then C, then D, then E, then F. In-order traversal says that you need to traverse the node after left subtree but before right subtree. In between both. In between both means put the dot for every node in between left and right subtree. Put the dot and do the same kind of traversal from left to right. Why left to right? Just because here we are traversing left subtree first. We are going from traversal direction left to right. Start the line drawing from root and go towards the root again, come back here and here. What is the sequence of dot this time? It is C, B, A, E, D, F. That is the in-order traversal. And for the post-order traversal, what I will have to do, what I'll have to do is, post means the node is traversed after left and right subtree both. So left and right subtree both means I'll have to put the dot at the end. Here. After left and right subtree, start from again root, take this line towards the border of every single node. Whenever the dot comes, print it. The sequence of dot gives you the post-order traversal. Post-order traversal this time is C, B, E, F, D and A. That is the dot method. It is easy when you go for the dot method. Why? Just because the dot method can give you the easy answer, simple way. Sometimes the tree is very large, you may get some kind of mistakes. You may get some kind of mistakes. Dot method can work easily. Or even if you are going with the direct method, sometimes you can verify your answer with this dot method. There are some observations, you all know those observations. Observation is the first symbol of pre-order traversal is always root and the last symbol of post order traversal is always root. सबसे पहले प्री ऑर्डर ट्रेवर्सल में जो भी ट्रेवर्स होगा वो हमेशा रूट होगा, सबसे लास्ट में पोस्ट ऑर्डर ट्रेवर्सल में जो ट्रेवर्स होगा वो रूट होगा. So let's go for another type of traversal, which is converse order traversal. What is converse order traversal? The general conventional traversal traverse the left subtree first. Converse order traversal says that we will start with the right. We will start with the right. So converse order traversal, same pre-order, in order, post order. Instead of traversing the left subtree first, we are going to traverse the right subtree first. That's the only difference. So converse order, pre-order traversal says we will traverse the node first here, yes, but after that we will go towards right subtree first, then left subtree recursively first. In the in-order traversal, we are going to traverse first of all right subtree, then node, then left subtree. And in the post-order traversal, first of all right subtree, then left subtree, then at the end node. Only thing is that we are going to have right subtree first before left subtree. In the converse traversals, same to same three type of traversals we have. So what will be the difference in the functions? I'm not gonna give you all the functions just because you are all intelligent enough to draw this particular thing. Converse pre-order, if I am calling with the pointer t, if t is true, what I'll have to do is traverse the current node. After that, recursively you call first for right child, then left child. And hence, for converse in order, what you will do? You will have this print statement in between the calls. And post order, this print statement will be at the end. Only that difference will be there. It's very easy, very easy. Okay, let's have the converse pre-order traversal of this, but we can go with the dot method here also. Yes, how? If you remember dot method, what it says, pre, pehle dot, for every node pre first dot, but the traversal direction has changed here. It starts from right and goes towards left, right? So starting from right, put the dot towards right of every node. And start the direction from right, go towards left. And have this complete round. This time the direction has changed. Why? Just because we are traversing the right subtree first. So direction has changed, put the dot first. Traversal converse order is A, D, F, E, B and C. Similarly, if you are putting the dots for in order like first of all right, then node, then left, in between left and right. But yahan bhi you will have to take care that you will have to start the traversal from right to left. This one. So what is the in-order traversal? F, D, E, A, B, C. And post-order traversal. At the end, from right to left, at the end of the nodes, you need to put the dots. Start from right, direction should be right to left. Dot sequence gives you the traversal. Traversal is F, E, D, C, B, A. F, E, D, C, B, A. That is the post order of converse type. But if you remember, such kind of dots too we have kept in normal general conventional pre-order. Yes, if you remember such kind of dots which we have put in converse pre-order, such kind of dots we have put in the general conventional post order. What is the difference then? The difference is direction of the traversal. If you will start direction from left to right, it becomes a regular conventional post order. But if you take right to left, it is converse pre-order. Left to right means reverse of this. So we will have one observation here. If you take reverse of converse pre-order, you will get the conventional post order traversal. If you take reverse of converse post order, you will get conventional pre-order. And if you get reverse of converse in order, you will get regular in order. प्री का पोस्ट, पोस्ट का प्री, बट इनका इन ही रहेगा रिवर्स में. Okay, now let's go ahead and let's see something else. Label order traversal. What is label order traversal? Level by level you need to traverse the nodes. Is there any standard? Few standards are there that you can traverse from left to right, every level left to right. But you can follow random order also. But remember, you traverse level number L. After that only you can traverse the nodes of L plus 1. Then next and next. So first of all, node of level number 0. After that, next level B and D you can traverse in any sequence. And after that, C and E and F, last level nodes. So these you can traverse in any sequence, these you can traverse in any sequence, but you need to traverse B and D both before you go for C, E, F. You need to traverse A before you go for next level B and D. That's the level order traversal. समझ पा रहे हो? अभी तक सब कुछ क्लियर है? चलिए अब बात करेंगे कंस्ट्रक्टिंग द ट्री यूजिंग ट्रैवर्सल्स. इफ यू वांट to construct the tree using traversals, then 2 traversal आपको चाहिए. 2 traversals are required, and among those one should be in order. You know why? Just because, see, pre-order and post-order can give you pre-order or let's say post-order. I should say or. दोनों में से कोई भी एक रहेगा आपके पास, can give you the root of subtree. Any tree, pre-order or post-order, can give you the root. But if you want to identify left and right subtree uniquely, that this is the left child, this is the right child, then you will need inorder. Inorder helps in what? To identify left and right subtree uniquely. But क्या? So how many traversals required? 2. Pre-order and in-order given, you can draw the unique tree always? Yes. Post-order and in-order given, you can draw the unique tree always? Yes. Pre-order and post-order given, can you draw the unique tree always? No. Sometimes yes. When? When? Pre-order, post-order can give you the unique tree when you have each node with 0 child or 2 children. अगर हर एक नोड के 2 चिल्ड्रन हैं तो आपको प्री ऑर्डर पोस्ट ऑर्डर दोनों मिलके और एक यूनिक ट्री दे सकते हैं. क्यों? जस्ट बिकॉज देयर यू विल नॉट हैव एनी प्रॉब्लम ऑफ लेफ्ट एंड राइट. If you have single node of any particular node, if you have single child, then that single child will go towards left or right. Pre-post cannot tell you. प्री और पोस्ट आपको ये नहीं बता पाएंगे कि एक जो सिंगल चाइल्ड है किसी नोड का वो लेफ्ट में आएगा कि राइट में आएगा. बट इफ यू हैव 2 चिल्ड्रन, yes, pre and post both can give you unique tree. So I am writing that pre-order and post-order can provide unique binary tree only when each node in that BT has 0 or 2 children, क्योंकि ये सिंगल चाइल्ड को आइडेंटिफाई नहीं कर पाएगा कि वो लेफ्ट में होगा कि राइट में होगा. Such kind of tree is actually called as full binary tree. We will see later on. उसको full binary tree बोलते हैं. राहुल, एक चाइल्ड भी तो हो सकता है किसी नोड का. तो अगर एक चाइल्ड हुआ किसी नोड का, तो अगर ऐसा बाइनरी ट्री है जिसमें एक चाइल्ड भी है किसी नोड का, तो वो प्री और पोस्ट से नहीं बन पाएगा. प्री और पोस्ट से वही पर्टिकुलर ट्री बन पाएगा जिसमें हर एक नोड के या तो 0 चाइल्ड है या 2. एक चाइल्ड वाला नोड ही नहीं है. नाउ लेट्स कंस्ट्रक्ट द ट्री यूजिंग ट्रैवर्सल. फर्स्ट ऑफ ऑल, प्री एंड इन. प्री एंड इन. प्री विल हेल्प मी गेटिंग द रूट ओनली. In will help me getting the left and right subtree only. Let's start. Preorder traversal, the very first is root. Very first is root. First symbol root, 1 is root. If I identify 1 is root, I can identify left and right of root through in order. How? Where is 1? Here. Before 1, whatever you traverse should go towards left. After 1, whatever you traverse should go towards right. That is the preorder traversal, in order traversal's definition. In order you traverse, first of all entire left subtree, then root. So entire left subtree 2, 3, then root, then 5, 4, 6 right subtree. Now let's go ahead. 2 and 3. First of all, only 2 and 3. Only 2 and 3. If you are checking, check out 2 and 3 in preorder to get the root. Which comes first? 2. Root is 2. Now you just check as compared to 2. Where is 3 in order traversal? Why? Left and right वहां से मिलेगा. In order 3 comes after 2, means should be in the right. Fine. Now 5, 4, 6. Check out 4, 5, 6 in the preorder. Which comes first? 4. Root. After that you go towards in order traversal. Where is 4? Here. Before 4 you have 5. So 5 should be in the left and 6 should be in the right. Right? So automatically you can get, if 2 is having single child, only 2 nodes are remaining. 1 will be root, 1 will be either left or right. Which one will be in the left and right? Root is 2. I can identify here. 3 is right. How I can say that? Just because 3 is traversed after 2. First of all left, nothing, then root 2, then right 3. Like this way I can easily identify. Sure. आगे बढ़ते हैं. Next is post and in. If you have post order traversal and in order traversal, how to identify the tree? Post order traversal mein we will have to check out the last symbol. Last symbol is always root. So last symbol always root. Can I get the root of the tree? Yes, A. I got the root of the tree, A. After that I'll check out in order traversal. Where is in order traversal? Here. I know that in order traversal, before the root, whatever you traverse is the left subtree. So A is traversed here. Before the A we are having EBF here in the left. Right side mein aayega DGE or DGC. Bifurcated left and right. Yes. Now do the same thing on EBF. Now you will have to check only EBF. Only EBF here. Which is the last symbol? B. So B is the root. Okay. B is the root. Fine. I can identify B as root of this left subtree. Now if B is root, go towards in order traversal. Check out where is the B. Here is B. Before B we have E, so left subtree is E. After B we have F, right subtree is F. Now next is what? Right side. Right side is DGC. DGC you check in the post order to get the root. DGC here. Last symbol is C. Okay, last symbol is C. Fine, got the root. Now let's go to the in order side. In order side, let's go and check out C. Where is C? Here. What is in the left? D and G both? Yes. Right side, nothing. After C, nothing. So D and G both will be in the left. D comma G. I have written. Now DG, how those will be arranged, I'll have to apply the same method once again. So let's draw the tree once again. A, B, C, E, F. Now DG, where is DG? Here. Last symbol, post order traversal, last symbol root, D is root. Now in order traversal says what? D is root. After that G is traverse, means G is in the right of D. Got it? चलो, अगर अब आपको कॉन्वर्स ट्रैवर्सल्स दे रखे हैं तो हाउ टू कंस्ट्रक्ट द ट्री. Converse traversals, if given, then you can convert those into regular conversions. Regular ones, कैसे? This is the post order. Yes, convert this into regular pre-order. Regular pre-order. You can do that. Yes, you can do that. How to convert this into pre-order? Regular pre-order. Post order. Converse post order का reverse is regular pre-order. Reverse is regular pre-order. What is a regular pre-order? 1, 2, 4, 5, 6, 3, 7, 8, 10 and 9. This is converse in order. Reverse that and you will get regular in order, which is 2, 5, 4, 6, 1, 3, 10, 8, 9 and 7. After that too works same to same. Works same to same. All those members who are still wondering how to draw the tree using pre-order and post-order, if I have brought the question here, we will do that. Otherwise, we are already running a series of special classes, right? Practice questions of tree. In the next special class, I will solve all those questions, pre-order and only post-order traversal. Okay, fine. Remember, any special class I am gonna take on topic wise practice questions tree. Next question pakka we will solve and I'll explain the method in the detail. Here I cannot explain the method. Fine, just because it's a revision section. Okay, let's draw the tree now. First of all, this is pre-order. Babu, it is pre-order now and this is in order now. Pre-order first symbol root. These are the left, these are the right. In the left 2, 5, 4, 6. I'll have to check here. First symbol 2 as root. No, I'll have to check here. What is root? Why? Just because pre-order gives me root. Root is 2. Root is 2. Root is 2. Left side root is 2. Fine. If root is 2, I'll have to check in order that which one is left and right. 2k, right में 5, 4, 6. Right में 5, 4, 6. Okay. Now I'll have to check again 4, 5, 6 here. What is the first symbol? 4. So 4 is root. Again go to in order and check out 4 के comparison में where are 5 and 6. 5 left, 6 right. 5 left, 6 right. Go towards right side. My left side is done. Right side 3, 10, 8, 9, 7. 3, 10, 8, 9, 7 these. Which is the first symbol in pre-order? 3, root. Then here all the symbols in the in order traversal left and right. Left में nothing, right में 10, 8, 9, 7. Right में 10, 8, 9, 7. Fine. Go back up and check out where are these 10, 8, 9, 7. 10, 8, 9, 7 above are in the order. Where is first one? 7. 7 is first one, root. Left में 10, 9, 8. So all the members are in the left of 7. 10, 9, 8. Now again go check out the root. 8 is root. 8 के comparison में 10 is in the left, 9 is in the right. You can go step by step. I have solved this question quickly just because I thought I have explained one particular question already. Then there is another method which I have explained, that how to construct the tree using pre-order and right child pointer. See, pre-order can give you root, but in order gives you the left and right. But if there is another method which can give you left and right, then will that be fine? Yes, fine. I want left and right, that's it. Either in order should give me left and right, or something else should give me left and right. If pre-order can give me root, left and right can be given by something else. Yes, can be given by something else, like this. These are the right child pointers. Right child pointers are given, and left subtree and right subtree will be easily identified for each and every node. How? Pre-order traversal, very first, root 1. Right child of 1 given, yes, 3. So 3 is the right child of 1. Between 1 and 3, whatever comes should be in the left subtree of 1. Now, what is in the left subtree? 2 4s 5. Fine. 2 4 5. Root is first symbol 2. Is there any right child of 2? Yes, 5. Between 2 and 5, whatever comes should be in the left of 2. 4. Root is 4. 3 ka right child? 6. You can see there are 3 right children. 1 ka 3, 3 ka 6. 1 ka 3, 3 ka 6, 2 ka 5. Yes. Pre-order traversal 1, 2, 4, 5, 3, 6. 1, 2, 4, 5, 3, 6. Same to same. So pointers are given. I know which node is having right child pointer, and using the right child pointer I can easily identify if this is the right child. In between right child and the node, whatever comes should be in the left subtree of the node. These are the questions to generate the tree. Then we have post order and left child pointers. Works in just opposite way but same to same. How? Root is the last symbol 1. 1 is root. Okay. Left child pointer given, 1 ka left child pointer 2. Whatever comes between 1 and 2 should be in the right subtree of 1. Should be in the right subtree of 1. Right subtree 7 4 3. Now in that last symbol is root 3. Left child of 4. Left child 4. Is there anything between 3 and 4? No. So no any right of 3. Now where should 7 go? Of course there is no any right of 3, we decided. Then left of 3 is 4. Yes. So 7 should be in the child of 4. Yes. Child of 4. 7 is left child of 4? No. Why? Just because not pointer given. Pointer is not given. No. So it should be in the right child of 4. 2's left child given? Yes, 5. In between 2 and 5, whatever comes should be in the right of 2. This is the tree. Why not unique tree without in order? Sometimes we cannot have unique tree without in order. Why? Just because if any node has one child, then pre-order or post-order both cannot detect that the child is left child or right child. The child is left or right. That is the problem, and because of that, what happened? We cannot draw the unique tree, but we can draw the unique tree using pre-order and post-order when we don't have any confusion of left and right. Both children are present or no any children present. So we cannot have a single child node. Yes, in that case, a particular tree can be constructed uniquely with pre-order and post-order without in order also. Shakir Riaz, no, that's not true. Next one, complete binary tree. What complete binary tree is? A complete binary tree is a binary tree in which every node has full label. Completely filled means maximum nodes, except possibly the last one. On the last, you have relaxation that you can have less than maximum nodes. But if last level is having less than maximum nodes, then too there is a restriction. Restriction is all nodes on last level should be from left to right. From left to right. This is an example of complete binary tree. It's a complete binary tree, yes. All the levels are full, last level is also full. If I want to keep last level less number of nodes, I should arrange these nodes from left, सबसे पहले leftmost, then next and so on. That is a complete binary tree. Okay, understood? Now there is a definition, strict complete binary tree. This strict complete binary tree says that you have all the levels full. Last one also. No any relaxation. That is strict complete binary tree. Then we have complete binary tree with maximum and minimum number of nodes with height h. That is a question, how to draw that. Look at this. Minimum nodes means this level full, this level full, this level full, yes. Last level only single node is present. Minimum nodes. Height is equal to 2, 0, 1. Okay, height is equal to 3. 0, 1, 2 and 3. Height is equal to 3. Minimum nodes how many? 1, 2, 3, 4, 5, 6, 7 and 8. So minimum nodes will be how many with height h? Minimum with height h is equal to 2 power h. Maximum will be same to same जो हमने binary tree के लिए निकाला था. Last level also having full nodes. H is equal to 3. Maximum. How many maximum nodes we can have? N number of nodes. Maximum with height h is equal to how many? 2 power h plus 1 minus 1. Same to same. चलिए नेक्स्ट, एरे रिप्रेजेंटेशन ऑफ सीबीटी. सबको पता है क्या होता है एरे रिप्रेजेंटेशन ऑफ सीबीटी. फर्स्ट ऑफ ऑल, आर एरे root we will store at 0, not 0 at 1. Root at index 1. Then any node at index I. For any node at index I, its left child we are going to store at index 2i, and its right child we are going to store at 2i plus 1. 2i plus 1. Good, nice. So let's say if we have, this is the array. In the array you can store complete binary tree. Yes. Why don't we store general binary tree? I'll tell you later. Let's say complete binary tree we have is this: A, B, C, D, E, F. This is the complete binary tree. Root A is on index number 1. Find then left and right child. A's left will be 1 into 2. Right will be 2 plus 1, 3. This B is at 2. 2 into 2, 4. Left child at 4. Right child at 4 plus 1. Left child at this. Like this way you can store. Or directly you can understand A is on 1, B 2, 3, 4, 5, 6. Left to right level wise level you can store continuously. You can provide the indexing from here also. 1, 2, 3, 4, 5 and 6. Now one thing I'm gonna explain you. If we are storing complete binary tree in an array, why don't we store a general binary tree in an array? In general binary tree, we don't have every level full, right? If we have the nodes like this, or let's say this is the worst case, how many nodes you have? N number of 4 nodes only. But array element first will be stored on index number 1. Its right will be 1 into 2, 2 plus 1, 3. 3 into 2 plus 1, 7. 7 into 2 plus 1, 15. Elements stored on the indexes will be 15. So if n number of nodes are there, array size will be equal to 2 power n minus 1. To store n number of elements in the array for general binary tree, for regular binary tree, any binary tree, we will require this much space, 2 power n space. Space complexity will be too much and remaining all the indexes will be empty. That's why we don't store the regular binary tree in the array. We store regular binary tree through linked representation. Rahul, array index starts from 0 in programming language C. I am not teaching you programming language C. I am teaching you data structure. I can take any array size or any array index. Now, next is full binary tree. Full binary tree says that a 2 tree, either 0 child or 2 children. Beech ka case nahi. There is no any node which is having single child. All the nodes will have either 0 child or 2 children. Every internal node having 2 children, either it is external node. That is a full binary tree. Right? Example. Understanding this. This. All these are having 0 child or 2 children. Nothing else? No. So in this particular case, if you will go for that handshaking lemma, I told you total number of leaf nodes is equal to total number of internal node with degree 2 or 2 children plus 1. Now every internal node has 2 children. So all the internal node plus 1 is equal to leaf nodes in the full binary tree. We know that total number of nodes are total number of internal nodes plus total number of leaf nodes. We can replace L by I plus 1. So capital N you will be getting by 2I plus 1. Or if you will replace I by L minus 1, you will be getting 2L minus 1. So in the full binary tree, if one thing is given, total number of nodes given, you can calculate internal nodes and external nodes both. If leaf nodes are given, you can calculate internal nodes and total number of nodes both. If internal nodes are given, you can calculate leaf nodes and total number of nodes. All you can calculate easily. And one more thing you will have to remember here. Every full binary tree always have total number of nodes odd. Number of nodes will always be odd. Always, yes, you can check out the diagram here. Or mathematically also I can say, look at this. Internal nodes into 2. Whatever internal nodes you have into 2 is even plus 1. External nodes into 2. Anything into 2 is even number minus 1 odd number. So number of nodes will always be odd. Always, हमेशा odd रहेंगी. आप ड्रॉ करके देख सकते हो. In this particular tree you have 3 nodes, 5, 7. Then we have on the similar pattern, this was a 2 tree. 2 tree means every node has either 0 child or 2 children. Similarly, we have 3 tree. Every node has either 0 child or 3 children. In this particular case, what I have written, L is equal to I plus 1. How I plus 1? Every node has 2 children. Every node has 2 children, internal nodes, right? So 2 minus 1. Actually, what I am trying to write here is 2 minus 1 into I. When we have 3 children, then how many leaf nodes I can have is 3 minus 1 into internal nodes plus 1, which ultimately gives me the formula 2i plus 1. As many as internal nodes we have into 2 plus 1 will be the total number of leaf nodes. Always yes for any 3-array tree. You can verify, Babu. Look at this. 1 internal node with 3 children, 2 internal node with 3 children, 3 internal nodes with 3 children. 1 internal node, number of leaf nodes are 3. 1 into 2 plus 1, 3. 2 internal node with 3 children, 1, 2, 3, 4, 5 nodes are there. 2 into 2 plus 1. If 3 internal node, 3 into 2, 6 plus 1, 1, 2, 3, 4, 5, 6, 7 internal nodes are there, or 7 leaf nodes are there. Yes, Advait. Now k-array tree. If in binary tree total number of leaf nodes are 2 minus 1 into I plus 1. For 3-array tree, 3 minus 1 into internal nodes plus 1. Then in k-array tree, where each node can have either 0 child or k children, how you can generalize the formula? Generalized formula will be total leaf nodes will be equal to k minus 1 into internal number of nodes plus 1. If k is 3, 3 minus 1. If k is 2, 2 minus 1, 2 minus 1 is 1. That's why you write L is equal to I plus 1 in binary trees, which is full binary tree. Good, Sabha. Nice. Now we have few more types of tree. Left skewed binary tree. What is left skewed binary tree? It says that we have every internal node having only left child. Every internal node, non-leaf node, has only left child. Nothing else, no. Right child will not be there, no. So example is this. What about leaf node? Leaf node can have right child. Oh, it's a trap. Leaf node will never have any child. So internal node will have only left. External node only 1, which will have only 0 child, nothing. Right skewed binary tree. Right skewed binary tree means every internal node can have only right child, like this. Getting it? आगे बढ़े. Next is expression tree. What is expression tree? Expression tree is facial expression tree, mathematical expression. In the expression tree, you denote an expression in the trees. But to denote expression in the tree, what exactly you do is this, that you put the operator on the root, the left child on the left subtree, and left child, or I should say left operand, and right operand you put as right child or right subtree. Example, suppose you have an operation a plus b. What is the operator? Plus root. In the left operand is a, right operand is b. You can easily, what? You can easily detect it? Yes. But if you have an expression which is little larger, let's say you have an expression a plus b into c, what you will draw first? What you will draw first? And for this, you will have to understand the precedence and associativity rule. Precedence and associativity rule. Precedence of plus and multiplication, whichever is higher should be solved first. Which one is higher? Multiplication. So multiplication should be solved first. Left is b, right is c. After that, this becomes the right operand for this addition. Left operand. This is what? The expression tree. Chalo. Let's draw the tree for this expression. First of all, we will check out all the expressions. All the plus, multiplication, exponent, division. Which is having higher precedence? Exponent. So first we will have to solve exponent. Let's solve exponent. Exponent, left operand 3, right operand 2. After that, which operator? Multiplication and division, both are having same precedence. So what I'll have to solve first? I'll have to solve first the left one. Associativity is left to right for multiplication and division. Multiplication, left one we will have to solve. Left is 7, right is this. This one is done. Now division. Division 4. So for division, left is this, right is 4. Ultimately, if this much is done, addition you can solve next. Addition, for addition, left operand is 2, right operand is result of this tree. For addition, left operand is 2, right operand is this result. That is the expression tree of the given expression. Let's draw the expression or the trees of these expressions. Minus b, these are actually the unary operators. And when you have unary operators, you know what happens? In the unary operator, you will have either left operand or right operand, only one operand. For minus b, what is the operator? Minus. What is the operator? Minus. So if minus is the operator, only one operand is present, right operand b. For log of x, what is the operator? Log. Only one operand present? Yes, x. For x factorial, operator is on the root factorial. Operand this time is in the left, x is in the left. Yes. Log of x factorial. First of all, you will have to solve x factorial. Solve x factorial. How you will solve x factorial? Like this. This result becomes operand for log. So how should I write? Factorial x first. This becomes operand for log. So right operand for log is this. These are the 4 trees.
It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging gate contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with the best.
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for gate till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack gate deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate gate challenge. Unacademy Combat. Register now.